Hi, my name is Karsten, and I'm a Principal Solutions Architect at Amazon Web Services. In this video, I cover how to test your application's performance on AWS Graviton. This is the third of 3 videos on this topic, and it completes the series. I covered how to run a containerized test harness to collect and extract metrics, logs, and traces from a performance test to AWS CloudWatch in Part 2. In Part 3, I'll discuss how you can use this data to draw conclusions from a representative sample to the larger population of instances in your production fleet. Specifically, I'll cover how to reason about observations in your dataset using basic statistical measures, how to compare results across 2 or more alternatives, and how you can ensure results are plausible and statistically significant. You might want to fast forward to skip this part if you are already familiar with statistical tools. This spreadsheet shows the results of running a decision support benchmark using the test harness introduced in Part 2. You'll notice that it contains a high number of individual observations. I scroll to the right to see the response time recorded during each of 100 iterations of the same query. I scroll down to see the different instance types and queries tested by my benchmark. Each entry represents a single measurement of system response time for a total of 33,000 observations. The dataset is organized by instance type and query, where the instance represents the EC2 instance used to run the query. In my example, I'm using a memory-optimized Graviton instance, and the query represents a particular use case, such as loading, filtering, or aggregating data stored in an S3 backend. I notice that the benchmark tested more than 100 different queries in 3 generations of Graviton instances. This gives me enough data to build a probability distribution. Let's take a step back to understand what we need to do next. I start with a short primer on using probability distributions to describe our test results. In my example, I use an XY coordinate system to plot observations I recorded during a test run, similar to what we just saw in the spreadsheet example. The x-axis represents the range of values observed in my sample data from 0 to infinity. The y-axis represents the number of times that I recorded this observation. In statistical terms, I am creating a histogram. Next, I use a process called binning to segment the range of observations that I recorded in my dataset into a predefined number of bins. In my example, the blue line represents such a bin. Its position on the x-axis indicates the range of values represented by this bin, and its height represents the number of times this value was recorded in my test dataset. Once I plot the remaining bins, I get a distribution that looks like a bell curve. You'll notice that the observations cluster around the center of the chart and then taper off to the left and right. This is a common feature of probability distributions and a key reason for why you should collect a sufficient number of samples. Otherwise, you might end up recording extreme values that do not represent the true distribution of outcomes for your performance test. Next, I color code the midway point of this distribution to indicate the arithmetic mean or average of the distribution. This is helpful because it gives me the central tendency of this probability distribution. In other terms, 50% of observations in my test fell to the left of that midway point. The trouble with performance tests is that they are never perfect bell curves. They tend to be skewed to the right with values concentrated to the left and a long tail extending outward. In this context, averages make little sense. I need to use a different statistical measure instead. In fact, I'll use one that's called a geometrical mean to accomplish the same as before. In my example, the orange bar represents the geometrical mean of the distribution. This statistical measure is reliable in scenarios where extreme values in the distribution would push the arithmetic mean to the right. To complete the picture, I can use percentiles to distinguish what's acceptable performance versus outliers. In my example, I used the P95 or 95th percentile to indicate that 95% of observations lie to the left of the orange shaded area. And I can use statistical measures such as standard deviation to study variability in my dataset. In my example, all observations in the orange shaded area fall within one standard deviation to the left and right of the sample mean. I'm interested whether different generations of Graviton perform better for a given query type. I've prepared a separate tab to calculate statistical measures using the dataset from before. The left-hand side shows me values for R6G. The right-hand side shows me values for R8G, a fourth-generation Graviton instance. Comparing the geo-mean for both distributions, I conclude that R8G offers a 26% performance improvement for Q19. This means queries of this type, on average, run 26% faster compared to instances from 2 generations ago. For context, Q19 is a complex SQL query that analyzes sales and returns data for a specific store and time period. It involves a multi-table join and large-scale aggregations, perfect for testing the CPU on my host system. I can now repeat this analysis for other query types to determine if it's worth upgrading my cluster to make use of these performance gains in production. To put all that we have learned so far together, this chart builds on the previous example and visualizes results as a violin chart using matplotlib, a Python library. In my example, the y-axis represents system response time, and in this case, lower means better. I see Q19, the query we just investigated before, on the left-hand side. The visualization tells me that for all observations recorded in my test run, R8G was the better choice. The right-hand side shows Q76, another benchmark query from the same sample dataset. This query is I/O intensive, and it combines data from several fact tables using the union all operator. In this case, my performance gain from a CPU upgrade is lower, given the I/O intensive nature of the query. This concludes my analysis, and it provides the foundation for a data-driven discussion with my team about whether we should upgrade to a next-generation instance type. Let's recap what we learned in each of the 3 parts of this talk. We started first with what to consider when making the switch to a next-generation instance type, in particular AWS Graviton. We then moved on to discuss how you can take the guesswork out of performance testing by using repeatable and container-native test harnesses. We then looked at a set of tools that help you generalize results beyond a single snapshot captured by your test environment. If you missed any of it, go back to the corresponding part and watch it again. So when you next think of performance testing, then try our sample performance lab. Instead of spinning up and tearing down test harnesses every single time, this will give you a more controlled and repeatable approach to performance testing. It encapsulates the first principles that I covered throughout this talk. Of course, I encourage you to adjust and use this test harness to optimize and adjust it to your own workloads. All you need is Docker and Kubernetes skills in order to get started. Thank you for watching, and good luck with your next steps from here.